Everybody, let's try to wrap up Unit 4, put a nice little bow on it. A recap of where we've been. Linear momentum we know is going to be conserved as long as the net external force on the system is zero, right? In the event of a collision, when two objects are pushing on each other due to Newton's third law, we know the force on each other is equal and opposite. And we also know that they're going to experience that force for the same amount of time. So while the individual objects are changing their momentum, the sum of the change in momentum for the system is zero as long as there are no other external forces on the system, like, for example, some drag or friction, or even if this collision is happening on an incline where the force of gravity is going to be accelerating our system. An impulse or a change in momentum, the equation sheet tells us that J is F times T, so force times time. But if the force is changing, if we have a dynamic force, we know that force times time is going to break down, right? It's just like kinematics. When acceleration is changing, the kinematic equations don't work. If the force is changing, we're going to have to do something a little bit different here. And the equation, force times time, implies that we're doing the area underneath of the force versus time graph, right? If the force is constant, then that would just be a rectangle. You would do force times the time interval. But if the force is changing, if it's dynamic, then we can just calculate the area underneath to get that impulse or that change in momentum. Okay. We also know that the name of a collision tells us a lot about what's happening with that collision. For example, an inelastic collision, the objects don't stick together. So this really is the majority of collisions. They don't stick together. The objects don't end up as one. So you have to track them separately after the collision. And in the event of an inelastic collision, momentum is still conserved as long as there are no external net forces on the system. However, kinetic energy is not conserved. So when objects touch, when they collide, there's going to be some heat loss. There's going to be some kinetic friction, especially when the material deforms. There's going to be a lot of heat there. So an inelastic collision is going to conserve momentum, but not kinetic energy. And then the worst thing for kinetic energy is a perfectly inelastic collision. So this is like the maximum amount of kinetic energy lost for a collision is when the objects stick together. So perfectly inelastic, if those words are used, you know that the objects are sticking together. So we have two objects before the collision, one object to track after the collision. We just combine the masses. This is also the same way that we would mechanically approach an explosion. Okay, so instead of materials starting separate and ending up as one, an explosion is all the masses are starting as one and they're going off in separate directions. So it would just be a reverse perfectly inelastic collision. So whether it's a perfectly inelastic or an explosion, it's really bad for kinetic energy. We know that there's going to be a lot of heat loss. There's mechanical energy turning into thermal, a lot of kinetic friction there. So if they stick together or if it's an explosion, we know that momentum is conserved, but kinetic energy definitely not conserved. Okay, and the last one is elastic. This is kind of an ideal scenario. It's not very realistic. I know a lot of textbooks like to use the billiards balls. The cue ball hits the eight ball, and it's an elastic collision where both momentum and kinetic energy is conserved. But I challenge you to think about that billiards ball, right? If you closed your eyes, could you determine at what point the cue ball hit the eight ball? Of course you could, because you could hear it. And that sound that's made that's some mechanical energy that got turned into sound. So typically this is not something that we would see in our everyday lives, a really elastic collision where kinetic energy is conserved, because we're always going to handle some kinetic friction and sound and things. But realistically, how could you see an elastic collision? Definitely atomic collisions, because atoms don't actually touch when they collide, and also something like a gravity assist, where you send a satellite or you send a spacecraft really close to a large planet in its orbit around the sun, and you borrow some momentum and kinetic energy from that object. So that's something interesting. If you want to look that up and read about that, a gravity assist is a elastic collision, even though maybe the word collision is weird there because they're not actually colliding. That would be bad for your spacecraft. Okay, but the mechanics work out where momentum and kinetic energy is conserved, or energy in general. Okay. All right. Center of mass is the one I do want to cover today. The average position of the masses in a system, right? This equation looks intimidating. It is really just a weighted average. And when I write it, I personally like to write it as the sum of the MIXIs over the total mass, because that's all this is doing down here in the denominator. When you see the capital Greek letter sigma, you know that's just a sum, right? So what this equation is saying is take each mass times its coordinate divided by the total sum of the masses. And that's all we're doing here. Take each mass times its coordinate. The momentum of the center of mass, when we say total momentum, we are really talking about the momentum of the center of mass. So if you just add up all the individual momentums, that's the momentum of this hypothetical point in space that represents the average position of the masses. And that's really what's conserved. So when the external net force is zero, when the sum of the forces on a system is zero, then the center of mass will continue moving at a constant speed. And that's what we really want to track, is that center of mass, okay? So how do we calculate center of mass? For a geometric shape of uniform density, that just means the material is even throughout. That's going to be simple. We're just going to locate the geometric center. So if for a rectangle, I'm just going to put it right there. I have seen on the AP exam historically a few times where one point on the exam was really simple. It said, here's this weird shape. Can you determine the center of mass? Very quickly, can you determine the center of mass? And what was on the scoring guide was you try to balance it on the tip of your pencil. That was it. You're looking for the balance point, because we know that the force of gravity collectively acts there at the center of mass. So if you can find that balancing point, you've found the center of mass. Okay. If it's a collection of masses, for example, I can't just take these two objects here and balance them on my pencil because there's a big gap between them. So if we need to calculate the center of mass between these two, we will need their distance. We will need to know how far apart they are. So I'm just going to use 10 meters. And then I also need to know their masses. So let's use 2 kilogram and let's use 6 kilogram. Okay, so you probably have a hunch of where the center of mass is going to be. If it's a weighted average, it's not going to be right in the middle because the 6 kilogram is larger, right? So it's going to be shifted over to the right towards the 6 kilogram, but we can calculate exactly where that center of mass is. The first thing we need to do is establish a coordinate system, right? So pick an origin. And I always like to pick one of my masses as the origin because it makes the coordinate of that mass 0. So I'm going to choose the origin to be here. You could also choose it to be the 6 kilogram. I don't, because that puts the coordinate of the 2 kilogram in the negative x direction. So I'm going to choose this guy over here on the left, and then I'm going to go through that equation. So the position of the center of mass is each mass, so I'll take the 2 kilogram, times its coordinate in this coordinate system, which for the 2 kilogram, it's just 0, plus the 6 kilogram times its coordinate. Well, in this coordinate system where the origin is here, it's got an x coordinate of 10 meters. So I've got 6 times 10 divided by the sum of the masses, which is just 8. So 2 times 0 is 0 plus 6 times 10, or 60 over 8. Okay? So 60 over 8 is, of course, that is now bigger than 5, where 5 would have been right in the middle. 60 over 8. We can do that on a calculator real quick. Let's see, 60 over 8. Getting 7.5. Okay, so the location of the center of mass in this coordinate system is 7.5. So we'll put it right there. Okay, and again, that should make sense because that's a weighted average, and the 6 kilogram is 3 times greater than the 2 kilogram. Okay, if we see something really interesting like a cluster of geometric objects, then we're just going to combine our two rules, right? If these are two rectangles of uniform density, then we can mark the center of mass of that rectangle by looking at the geometric center. We can mark the center of mass of this one by looking at the geometric center. Now, if this were like a 12 kilogram and a 17 kilogram, okay, what I'm going to do now that I've marked the center of mass of each of those objects is I'm going to imagine that all of the mass is concentrated right there at that center of mass. And then I'm just going to go back to how do I calculate the center of mass between two masses. So if I got a 12 kilogram and a 17 kilogram, I know the center of mass is going to be somewhere along that line. I don't expect it to be right in the middle because the 17 kilogram is larger. And then I will find that the center of mass is over here closer to the 17 kilograms. So I just did that qualitatively so we could do that very quickly. But if I had, for example, the distance between them, I could calculate that number directly. Okay, but it's just combining those two rules. All right. The reason we want to identify the center of mass is really because I know what College Board is going to do. They are going to give you some really complex motion. They are going to try to describe this wild motion that just sounds impossible. Okay. For example, just an asteroid floating through space. And I know, one of the things that they've tried to do is, consider blowing one up so that, blow up an asteroid in space so that when it reaches Earth, it's the pieces are small enough that they'll just burn up in the atmosphere, something like that, right? And it's like, wow, that seems really, really complicated. I mean, how would you do something like that? And my advice to you is, the more complex something gets, the more complex the motion is, literally take a step back. Take a step back and just focus on the center of mass. That's it. Just focus on the center of mass, because we can predict the motion to a really great accuracy by just looking at the center of mass, by drawing the free body diagram of the system, and that represents the free body diagram of the center of mass. So I'll give you an example that shows up a time or two on the AP exam, and that's like a spring that's not just sitting on a table oscillating back and forth. If we were to do something really complicated with a spring. So I've got this spring where the gray area right there is the center of mass between this blue bob and this red bob. The blue one is much larger, so the center of mass is shifted over towards the blue. And what I'm going to do is I'm just going to throw this spring up into the air, right? And you can imagine College Board describing this motion. The spring is oscillating back and forth. It's also rotating. So lots of complicated issues that are happening, right? So this is something that is overwhelming. I'm seeing the motion of the red object, the motion of the blue object. I can't even track them both simultaneously. So yeah, this is where I might just give up, right? But here's what we're going to do. This is very, very complicated motion. We're going to step back. We're going to take a step back, a physical step back, and we're just going to focus on that center of mass, right? So the spring was thrown into the air. It was oscillating. It was rotating. It was a lot of really complicated motion. But if you notice, that gray dot followed this trajectory right here. That little parabolic trajectory right there is the motion of the center of mass. Now, when that spring left my hand, after I threw that spring into the air, it was oscillating, it was rotating, there was a lot going on. But what does the free body diagram look like? The free body diagram of the center of mass is just the force of gravity. So when this spring was traveling through the air, it was just a projectile. That's it. It was just a projectile, and it followed this parabolic trajectory exactly as a ball would have done, back in Unit 1. So again, when it seems really complex, when it seems really challenging, you're going to take a step back and you're going to look at the center of mass, and you're just going to focus on that center of mass and see what you can do with it. Okay? All right. Last one I want to look at is, what will happen if momentum is not conserved? So an example like this, where I've got a much larger blue object we'll call it a cart, that's going up the hill, and it's going to collide with this red object that's traveling down the hill. The first thing I would want to do is mark the center of mass. It's not going to be right in the middle because the blue object is much larger. So I'm going to mark it over there. And then I would consider drawing a free body diagram of each object. And in this case, let's call this a frictionless ramp. So my free body diagram for the blue one, of course, it is heavier. So I have a bigger FG. Let me just call it FG blue and FG red. So I'm not trying to indicate there that those are the same. And then let me call that FN red and FN blue. Okay, so consider your free body diagram of each object, and then consider the free body diagram of the system, right? Which is where we take all the forces and add them all together as if they were just on one free body diagram. And if I were to do that, you would notice that the sum of the forces on the system is just the downhill component of the blue and the downhill component of the red. So I'll just go ahead and mark those components. So if you don't remember how we broke those up, the downhill component of the red and the blue are what's causing my system to accelerate. So I could, using Newton's second law, I could determine the acceleration of this whole system. What does that mean? I mean, this is a complicated motion. The blue object is going to go up, the red object is going to go down, they're going to collide. Whether or not they stick together, it hasn't been, I don't know what type of collision it is yet. I would need to know if it's inelastic or elastic. But the one thing I know is this, that green hypothetical point in space, it is going to accelerate down the ramp. That's the one thing I know. It's going to accelerate down the ramp, and the acceleration is going to be the downhill component of the red plus the downhill component of the blue divided by the sum of the masses. So no matter what happens in this collision, I know that this green, it has an acceleration that's down the ramp. Now, because the blue object is larger, it does have a larger initial momentum. There's a larger initial momentum than the red one. But again, all of that complicated, what's happening at every moment, the one thing I know is that this green hypothetical point in space, the center of mass, it is accelerating down the ramp. Okay, that doesn't mean that its velocity is initially down the ramp. It just means that the acceleration will be down the ramp. I could determine the velocity of that center of mass by determining the total momentum. When we say total momentum, right, when we take the momentum of the red and the momentum of the blue and we add them together, what that really is the momentum of the center of mass. So the total momentum of the system is the momentum of the center of mass. So two things we're saying here. I could determine the initial momentum by adding together the red and blue momentum at the beginning. That is the momentum of the center of mass. And then I also know that since the sum of the forces on the system is not zero, that A, the momentum is not conserved, right, because we have an external net force, and that B, the center of mass is just going to be accelerating down this way. And I can even calculate that acceleration, okay? So the more challenging, the more complex the motion gets, I just want you to step back and I want you to track the center of mass, okay? All right, so that should do it for Unit 4. Thanks for watching.